Okay, I think we're ready to go. So I keep forgetting to announce this, but there's one mistake on the exam, and if you don't have your Scantrons now, that's fine. You can bring it back another time. On number 8, on the that doesn't work. There we go. That barely works. Number 8. No, sorry, not 8. 9. It's right next to 8. So it's the one with the picture of the two compounds. And number 9 was which formula best represents compound A. I miscounted, so I think on my key I put E, but the actual answer is C. So if you actually put C on there, just bring it up and I can regrade it and give it back to you later. And if you don't have it now, it's fine. For people watching at home, I know there's at least one. Bring it in when you can, and I'll appreciate the grade. Yeah, start a pile, sure. So it'll be 2 extra points. Yeah, you can just put it right out. Start it there. It's all good.
Do you want the test book up here or just?
Nah, just the Scantron is fine. Doesn't matter. All right.
Yeah, that one did kind of confuse me. I was like, that should be C, right?
Well, you should trust your instincts. You'd be like, why is this wrong? And then ask me. Somebody else asked me, and I realized I was dumb.
I put a big old question mark next to that because I should be right, but that turned out to be so.
I did the key a little bit too quickly. That's all. Anyway, so there's that. We did not have time to grade your quizzes yet, so that's in the works. We have a quiz this Wednesday. It'll be shell model, subshells, all that stuff. The stuff we went over last week. Anything that goes with that. So I think core charge, all that stuff. So, but now we're starting something slightly new. So this week we're going to kind of devote ourselves to the quantum mechanical model of the atom. I'm going to admit that a lot of this stuff is going to be just brushing the surface because we can't really dive too deeply into a lot of the whys. It's going to take, number 1, better math than we're mostly equipped to do, and 2, there's classes devoted to this topic. So we're going to brush the surface. If it seems not enough, then take more classes. That's all I can say about it because it's actually quite complicated. In fact, I am probably not prepared to do a full lecture on exactly all the whys of what we're going to talk about today. So I'm going to get as close as I can without overstepping my bounds and without going too far into the weeds because some of this you're not going to be like, okay, just accept it and move on. So let's review a little bit before we start. So what we went over last time was the subshell model. And we kind of just, hey, this is it. We didn't really build up to it too much, but we've got these S, P, D, F subshells that are within the shells. Those are the main ones. And they actually go in this order of energy. So S is lower than P, P is lower than D, D is lower than F, and so forth. But it's not as simple as, 1s is lower than 2s. Well, that's true, but there's like a 4s, which is lower than a 3d, even though 3 should be lower than 4. It gets complicated. So we learned a technique for memorizing, or not memorizing, but be able to figure out the actual orders of the subshells. So yeah, some of the energies of the subshells are close. So even though we have these subshells, 2s and 2p are different subshells, their energies are still close, somewhat close. And so when we consider, the distance of the electron to the nucleus, they're about the same still. There's going to be slight differences, and again, this is kind of more detail that we're not going to get into. But a lot more nuance, let's put it that way. It's not as simple as our shell model from before. But the energies for the shells are still quite different, okay? And again, there's some exceptions. This is 4s and 3d, you know, which are similar. But we'll get to that. So we went over this. We went over how to figure out the subshell ordering using the periodic table by ordering it by blocks. Don't forget, in the fourth row, you start with 3D, not 4D. In the sixth row, sixth period, it goes from 6S all the way down to 4F, then 5D, then back to 6P. So there's a little bit of, you know, you got to remember to count down in shell numbers in a couple areas. But otherwise, the periodic table is a great cheat sheet. I think we did this. So we did condensed electron configuration, or noble gas electron configuration. The idea is replace the first part of the noble gas, the first part of the electron configuration with a noble gas, where the noble gas's electron configuration is exactly the same. So in this case, D is the answer. So the helium noble gas here actually has a 1s2 electron configuration. So this was originally 1s2, 2s2, 2p1. That was the entire electron configuration. It's a little bit silly to replace 1s2 with helium, but that's what you can do. There's a little bit more ones that make more sense. But basically, the noble gas shortcut is just for replacing really long electron configuration lines with a short thing, like the noble gas with a bracket around it. We also did the ions. So ions, again, that's when you take away electrons or add electrons, depending on what kind of ion you're making. When you take away electrons, they have to come from one of the shells, one of the subshells. When you add electrons, they have to go into a subshell. So you have to know how many electrons a subshell can hold, when you have to add electrons to the next subshell, and so forth. So we can figure that out from the periodic table too, right? Group 2, 1 and 2, the S block has 2 electrons max. The P block has 6, you can figure it out from how many columns there are. The D block has 10, the F block has 14. Anyway, when we looked at the ions and their electron configurations, I think we glossed over this a little bit, but the cations and the anions had electron configurations that looked just like a noble gas. So somehow forming that electron configuration just like a noble gas was the ideal state for those ions. Cations tended to look like the noble gas before them, so potassium plus would look like an argon. And then anions tended to look like the noble gas that comes after them. So selenium, Se, becomes krypton when it becomes Se2 minus. That doesn't become krypton, I should say. It has a noble gas electron configuration. It has an electron configuration just like kryptons when you add 2 electrons. So, there you go. Calcium 2 plus looks like argon. Sulfide looks like argon. They are isoelectronic. That's another term you guys need to get familiar with. They have the same number of electrons. We did this too, I'm pretty sure. The electron configuration for rubidium ion, and I'm pretty sure some of you guys answered that one, D. Well, that would be the electron configuration for rubidium neutral atoms. The ion, you take away that one electron that's in the S subshell, and it's now just looking like the krypton noble gas. So it's got an electron configuration just like kryptons. Okay. So, I think at this point, this is where we started looking at some new stuff. Because the shell model, the new shell model with the subshells, even though that works really, really well, it's still using a naive way of thinking about how electrons behave. So yeah, we understand their energies. We understand they have some kind of order to energies. They're quantized states of energies, you know, so they have specific energies and that's it. But if we talk about like what they actually look like, what they're doing around an atom, again, it's not planets around the sun type of thing. It's something a little bit different. So these energy levels that we have seen with experiments. They exist, but they're not like shells. They're not literally shells around a nucleus. They're not like the electron is in this shell, and that's where it is, and that's it. It's more complicated than that. Okay, so we need a new way of thinking about electrons to kind of get to the nitty-gritty of really how they behave. And this is where quantum mechanics come in. So we've applied, so we've done the opposite. We've taken light, which we've originally thought of as a wave, and turned light into a particle, the photon, in order to explain a lot of things. That's what we're going to have to do with the electron. We're going to go the other way, though. Electrons are particles. They have mass. But we're going to apply wave mechanics to them. We're going to pretend, or not even pretend, we're going to treat the electron as a wave, which is really weird. It's hard to visualize that. So this is where really the math comes in. And really the only way you can describe it accurately is with mathematics. We're not going to do that. I think I showed you that double slit video just to kind of show you the weirdness of what electrons do. There's another great website. It's based in France, but I think there's an English translation. And it's got a few quick videos you can explore. So for instance, that one, I think this works. Just to kind of give you an idea of what here, I'll show this to you in a second. This is not going to make much sense yet, but let me stop there. So you guys can explore that if you like. It's kind of neat. There's a little bit of text to go with it to kind of read it, just nice quick explanations. But let's start off with this idea. We know that waves diffract, and you know, when you send light waves against a barrier with little slits in them, they will diffract through the slits. If you have more than one slit, like a diffraction grating does, those waves that emanate from the slits, that diffract from the slits, will start to interfere with each other and make an interference pattern. Light and dark, light and dark, okay? So we saw that, we've seen this before. And it turns out electrons do exactly the same thing. So that video we saw before, we did see that. So electrons do the same thing, which means they have wave-like properties. Because, you know, if you do the same thing with baseballs and a little two holes in a wall, they won't do that. They'll just make 2 points where they come out, and that's it. So if electrons can behave like waves, what does that mean in terms of how we think of electrons overall? So we have to think of them as delocalized, and that's a term that chemists like to use a lot. It basically means we're not going to say the electron is in one place and one place only. They're not localized to a specific area. They're delocalized, meaning they're spread out. That's all that means. The electrons are kind of spread out into an area of space, or a volume of space. Smeared out is another way to think of it, okay? So delocalized, you can't say they're just here. They're spread out. That's what delocalized means. It's a weird idea for matter, but that's the way we're going to think of it. And so when you visualize what would that look like, instead of thinking of the electron as a point, it's here, you can imagine it as a cloud of electron density. So imagine it as a cloud, and we're going to talk about the shapes of the cloud later, but if you had a spherical cloud that was darker in the center and got lighter as you went further away from the center, the darkness represents how dense the cloud of the electron density is. The lightness means it's less dense. And that density is a representation of where you're most likely to find the electron. So where the darkest parts are, that's where you're most likely to find the electron. Where it gets lighter, you're less likely to find the electron, but you're still able to find it there. That's kind of how we think of electrons, is this just cloud of electron density. So, you know, how is this possible? You know, if if you think of a wave like on a string, you pluck a guitar string, you don't say that the wave is on any part of the string, it's over the whole string. And that's kind of how we have to think of an electron. The electron is now behaving like a wave, and so it can't just be localized to one place. It's going to be all over the atom, okay? Yeah, so it's not really at one point, it's spread around. Okay. We know that electrons can have different energies. We've kind of seen that already with energy levels, and that's where our emission spectra come from, the transitions of an electron to different energy levels. So how do we kind of square that with, this picture of an electron cloud, this smearing of electron? Well, we're gonna define it as the electron being able to be in different regions of space, not just an orbit, but like a whole region. So when it has a certain energy, it can be in a bigger region of space or a smaller region, or we're going to talk about shapes too, but that's kind of how we think of the energies now. And these different energy states are going to be characterized by, again, distance. So the whole kind of distance from the nucleus does apply, but it's not going to be a set distance. It's going to be a range of distances, okay? Momentum is, if you haven't taken much physics, it's not going to matter to you too much. Think of momentum as an analog to energy. So just kind of to give you an idea of what momentum is in physics, if you're in space, okay, and you push a baseball, the baseball will go pretty easily, but if you are, well no, let me give you a better example. Momentum, if a baseball is coming to you at 50 miles an hour and you get hit by it, it'll hurt a little bit. If a car is coming to you at 50 miles an hour, it'll hurt a lot, okay? The car has a lot more momentum, okay? It's a combination of the speed and the mass that drives the momentum, and it's a little bit related to kinetic energy. So let me put it that way. That's what momentum is. If you don't like the word momentum, just think of it as an analog to energy. The more momentum something has, the more energy it has. It's not exactly right, but that's the best way to think of it if you haven't done the physics yet. And then locations of stability in space. So it's not going to be just distance from the nucleus, it's going to be different areas around it. So it might not be completely symmetrical, spherical. It might have, maybe if you have a Cartesian coordinate, x, y, z, it might be more stable in the z direction than the x direction or something like that, okay? So there's going to be lots that contribute to how we define an energy state for an electron. So another thing, and this is again, we're brushing the surface, is something called Heisenberg's uncertainty principle. And it's a consequence of the mathematics that we're using. We're not using it, but that developed the quantum mechanics. So Heisenberg's uncertainty principle, it's kind of a balance between this concept of a matter and a wave. So with matter, your particle is localized, right? You know where it is. But if you have a wave, you can't define the wave as being here. It's delocalized. So as a consequence, when you're talking about an electron that has characteristics of both matter and a wave, Heisenberg came up with this equation that kind of set a limit on the understanding of the electron as a particle or a wave. So what this is right here, this delta, it's not change in x, even though that's what delta normally means. It's the error in the position. So this delta x is a max error in the position. So I guess the way you want to think of it is how certain are you of the position of the electron? So the more certain you are, the smaller your error in understanding the position. The more certain you know, hey, I know the electron is right here, then you have a really small delta x. That's what that is, an error in the position. I have no error in the position. I know exactly where it is. This is, in physics, this is momentum, mass times velocity. And like I said, if you have a hard time thinking in momentum, just think of it as energy. So what we have here is uncertainty in the error of the energy calculation. Do I know exactly what the energy of my electron is? If I know it really well, then I have a small error in the momentum. If I don't know the energy very well at all, like it's in this range, but I don't know exactly what it is, then I have a larger error in the momentum. So that's what those two terms are: error in the position, error in the uncertainty, in the momentum. These two errors, these two uncertainties, have to be greater than this constant, greater than or equal to. So Planck's constant over 2 pi. That's some number. You can calculate if you want. There's some number. And the idea is you can never know both the position and the energy or momentum with 100% certainty. You can't know them exactly because the two errors together have to be greater than this number here. So what is the result? You can know the position of an electron really well and then know very little about the energy, or you can know the energy really well and know very little about its position. Or you could know a little bit about each, basically. So there has to be a balance of error in those two terms. And that's just a consequence of dealing with particles that have both particle and wave properties, okay? All right, so that's Heisenberg's uncertainty principle. Forget that. So we can never be certain of the position and its energy at the same time. Yeah, we pin down the energy, we don't know much about its position. If we pin down the position, we don't know its energy. Okay, so like I said, it's a balance. We don't want to know nothing about one and everything about the other. We want to know a little bit about both. I'm going to skip that because that's long. So, this is where we do a lot of hand waving. And I really encourage you to take more classes if this is somewhat interesting to you, because it's crazy. The math involved is a little bit difficult, but you can get through it with enough patience. These are, when you do, when they give you homework for these classes, this is kind of homework where one problem takes like 8 pages to do. Like just 8 pages of equations and stuff. It's crazy. Anyway, if you like to torture yourself, feel free to try that. So, Schrodinger came up with an equation that describes the movement of an electron. And it's a complicated equation to use. We're not going to solve anything. We're just going to look at the results. So you can solve his equation. For hydrogen, you can solve it exactly. You can get precise results. For anything else, you can get approximate solutions. So that's how difficult it is. So the solutions to the Schrodinger equation are called wave functions, and they have this symbol. This is the Greek capital letter psi, and that's the standard variable we use for a wave function. These wave functions kind of are created using different parameters. And so we plug in different parameters and we get different solutions. So different wave functions, okay? These parameters that get changed, one of them you're familiar with, n. That is the quantum number. That's the principal quantum number, it's called. We know it as energy level. We know it as shell number, same thing. But then there's these other ones. There's L, that's a script L, and then there's an M with a subscript L. These 3 quantum numbers are going to be, we're going to look at them in a second. And they are parameters that we use to get these different wave functions. These are just equations that describe the motion of an electron. So depending on the parameters, you get different wave functions, different equations. Now, these wave functions by themselves don't really mean anything physically. So you can't say the wave function means this. It doesn't have any meaning by itself. But you can transform these wave functions to do a lot of different things. So one of the simplest transformations, and I don't mean simple that it's easy to do, but if you square the wave function, you get what is called a probability distribution. So now the wave function will tell you the most likely positions of your electron, where you're most likely to find an electron. So that's kind of like what quantum mechanics does for us. It gives us these equations. These equations let us kind of map out where we are most likely to find electrons. And they require these different parameters, these quantum numbers, that are, well, we know n so far is integers only, right? Starting from 1 to infinity, and that's it. So, a little bit into how this works, just to, if you're, whet your curiosity if you're curious. This is the infamous particle in a box experiment. So here's what I'm going to say about this. We're thinking about 3D, right? Electrons flying in regular 3D space around a nucleus. That's too complicated. Let's boil the problem down to one dimension. All right, so instead of x, y, and z, just think of x. That's what the particle in a box experiment is. It's looking at a one-dimensional universe. We're trapping our electron in a space. It's called a box, but really it's just a boundary on two sides. So here's a length, distance, and we're trapping the electron inside this area. It can't go out. And it turns out that the only solutions that make any sense for this kind of experiment are what are called standing waves. These are waves that kind of fit the box exactly. So you get one like this, you get one like this, you get one like this. Anything like where the wavelength's a little bit longer, then the wave doesn't fit exactly in the box, and it doesn't work. So I'm just going to leave it at that. It doesn't work. So again, this is one dimension, okay? So the wave function by itself doesn't really mean anything. But if I square it, so if I square that, I get this. And the squared version indicates the likelihood of finding an electron at that position. So here I can see that I have a really large chance of finding the electron right in the middle here. With this wave function, I have a chance of finding the electron here or here equally, but no chance right in the middle. So that, I'm just kind of overall saying this is what the math does for us. This is the one-dimensional solution. This doesn't work for our case. We're 3D. But that's kind of like a simplistic kind of what we do in quantum mechanics with wave functions and stuff. So I'm just going to scare you a little bit. This is what one of Schrodinger's equations look like. And this is a version of it. There's many versions. There's a version where we don't care about time. There's a version where time does matter. It's complicated. Like I said, even me, I'm not at a level where I can explain this with absolute certainty to you guys. So let's skip that. This is just kind of, if you want to horrify yourself a little bit. We got second derivatives, all sorts of fun stuff in here. Anyway, and again, you can't solve this except for the hydrogen atom. Like, for other atoms, it's unsolvable. You have to do approximations. So if you've ever done that math yet, it sucks. So, just the bottom line here. The wave function, this psi wave function, has no physical meaning. So it's the psi squared that gives us probability of finding an electron. And so again, why do we talk about probability? It's because of Heisenberg's uncertainty principle. You can't say for sure where an electron is going to be. We can only kind of predict a likelihood of finding an electron in a certain area. And the parameters that define the wave function, and we know this one already, but there's two others. These are the quantum numbers. And that's kind of what we're going to take a look at next. So, the first one, we know it as the principal quantum number. We know the rules for it. It starts at 1, it goes up to infinity. And we kind of, in general, know what it means so far. Before it was the shell. What did the shell tell us? The shell tells us how far the electron could go from the atom, right? The larger the shell, the further the electron can go. It's the same idea here. The n gives the size of the region in which we're allowed to find the electron. So let me go back and make sure again. These wave functions, these solutions to the Schrodinger equation, these are describing where the motion of an electron around an atom. So it describes where we're likely to find an electron. These are actually called orbitals. We don't call them orbits anymore because orbits are planet around the sun. It's not the accurate way to, it's not an accurate name for it. So they're called orbitals now. And again, n tells us the size of the orbital. So if I have a larger n, that means my orbital is bigger, my electron can be further away from the nucleus. Now the new ones, L. L is called the angular quantum number, or angular momentum quantum number. And it has specific rules that are based on what n is. So that's what makes it a little bit more complicated. So L can be all of the integers starting from 0 up to n minus 1. So the idea is if my n is 1, then L can only be 0, and that's it. Because n minus 1, 1 minus 1 is 0, that's the max. Does that kind of make sense? If my n is 3, then what can L be? L, can be all the numbers from 0 up to n minus 1. Well, n minus 1 is 2. So all of my L's are going to be 0, 1, and 2. So again, L depends on what the n is. You have to define n first, and then you can say what the other L's are. Now, what does L tell us about the orbital? L is the subshell, so we know that already. But what is a subshell really? Well, it's got a slightly different energy, right, than other subshells. But in terms of orbitals, what that tells us is the shape of the orbital. So when you have L is equal to 0, that is the mathematical equivalent for an S subshell. When L is 1, then you're talking about a P subshell. When L is 2, it's a D subshell. When L is 3, it's an F subshell. And these subshells, we haven't considered their shapes yet. They have shapes. An S subshell is spherical. It's not a circle. It's a sphere, 3D. A P subshell has this dumbbell-looking shape, and depending on the artist who's drawing them for the textbook or whatever slide, they're going to look slightly different every time. This is a very common shape to see because it's easy to draw on a board, like that. But sometimes you'll see them written as like little globes like that. One globe here, one globe. It really depends on the artist. But what's common is that it's 2 lobes. And there is nothing in between it. Notice there's 0 electron density right in the center. Okay? Okay, and then D, and we'll see F in a second, but F is quite more complicated. The last one is M sub L. M subscript L, so we just say M sub L. That is the magnetic quantum number, and again, it depends on the previous quantum number. It is all of the integers between L and minus L. So if your L is 0, then your M sub L is only going to be 0. All the integers between positive and negative 0 is just 0. If your L is 1, then your M sub L is going to be every integer between minus 1 and 1, which is just minus 1, 0, and 1. And it keeps going like that. So 2 is going to be minus 2, minus 1, 0, 1, and 2. So what does M sub L mean? There's two things it tells us. One is the number of subshell orbitals there are. Number of orbitals that are in that subshell. So in subshell 0, L is equal to 0, that's S. In the S subshell, there's only one kind of orbital, 1. The fact that there's only one number here means there's only one orbital. In subshell P, right, when L is 1, that's a P subshell. There's 1, 2, 3 different orbitals. That's what these 3 numbers mean. 3 different orbitals. And they are 3 different orientations of the orbitals. That's what makes them different physically. So this P-shaped orbital, this one points in the z direction. There's a second one that points this way, left and right. And there's a third one that goes in and out. Those are the three orientations. So with the D subshell, there's going to be 5 orientations. With the F, it's going to be 7. We'll cover that in a second. So these are the 3 quantum numbers that define what your orbital looks like, this region of space where the electron is allowed to exist. So, N is the size, L gives you the shape, M sub L gives you orientation. You need all 3 to describe an orbital. And so if I were to tell you, hey, a 2p orbital, and in addition we're going to include the direction it's pointing in the x direction. So if you have the 3-axis Cartesian coordinate, this one's pointed along the x-axis. What are the quantum numbers that correspond to that subshell? Well, it's n is going to be 2, because that's the number of the shell. L is going to be 1, because that's the number for a p orbital. Right? L is going to be 1. And then finally, the x, which is the direction it's pointed in, the orientation. We're not going to have a way to define, oh, x is this one, or x is this one. We don't know that. But x tells you that it's one of these 3, basically. There's going to be px, py, pz in this case, and they're going to correspond to one of these M sub L numbers. We don't know which one is which, okay? But it corresponds to one of them. Okay. So given now all this information now, we can kind of explore the different orbital shapes. These are all s orbitals. And s orbitals start with shell 1. Yeah, there is a 1s orbital. We know that from the periodic table. And there's a 2s and there's a 3s. And what is the difference between them? They're all round. They all have just 1 orbital per subshell. But the sizes are different. And as you go higher in energy levels, higher in n, they get bigger. And so there's the 3 of them together, kind of to show you their size. Now again, we're talking about these orbitals are regions where we are likely to find an electron. And we're supposed to think of them as electron kind of clouds, where the density of the cloud determines how the likelihood of finding the electron. In reality, there's no boundaries. They kind of just fade away as we get further and further away. So to make things simple, artists and chemists, of course, define boundaries as kind of like where you're most, like 90% likely to find an electron. Boom, we set that as the boundary, and then we kind of draw a hard boundary, which is why these are kind of hard circles, right? They end. But in reality, they don't end. They just kind of fade away. As you get further away, you get less chance of finding the electron. So just kind of keep that in mind when you see these pictures. All right. Now, another thing, and it gets complicated. Those wave function diagrams, and you do psi squared, which is the probability of finding the electron. They get complicated. We're not going to worry about it too much, but for a 1s, okay, so here's psi squared, and here's the radius from the nucleus, distance from the nucleus. For a 1s orbital, it kind of does this, and that's it. So you have a really large chance of finding it close to the nucleus or at the nucleus, and as you further away you get, the probability decreases. It kind of goes to, what is it called? Exponential or logarithmic? Whatever it is, it kind of fades away to infinity, kind of like that. And the 2s and the 3s have a similar feature, but if you actually draw this out, and again, we're not going to worry about it too much, but just to kind of give you an idea of how complicated it could be, the 3s diagram kind of looks like this. Maybe I'm drawing it wrong. Anyway, it does something like, I think it actually goes down all the way. So, like that. So you still have a really high chance of finding it in the nucleus, but then there are these secondary areas here where you can find it. And then there's these regions where you're not at all likely to find the electron. Right? Here the electron density is 0 and 0. And that's what you're seeing here. These are what are called nodes. These are areas where you definitely cannot find the electron. That's just what the math tells us. It's still a spherical orbital. So if you look at it as a whole, it's still spherical. It's still bigger. But, you got to kind of dive into it a little bit in detail. There's some significant differences, okay? Again, we're not going to worry about it too much. This is not kind of a thing that we need to worry about in our class. But there's a lot more to orbitals than we're going to get to. Let's put it that way. So here's a p subshell. And p subshells, unlike s subshells, where you have a non-zero chance of finding the electron at the nucleus, p subshells, you have 0 chance of finding the electron at the nucleus. It just happens, that's how the math works. And that's kind of why they're shaped like this. There's kind of a nothing in the center. It's like there's no electron density right in the center. And it just, the math works out that there's 3 different p orbitals, 3 different orientations. And so one goes in the x direction, one goes in the y direction, one other goes in the z direction. And there is a nodal plane at the 0 point, where you have no chance of finding the electron. If you put all 3 together, that's kind of what all 3 of them look like together. Those are just regions where you're likely to find the electrons that are in that p orbital, in that p subshell. Okay. So d orbitals are a little bit more crazy looking. Where p orbitals had 2 lobes like this, d orbitals tend to have 4 lobes. So there's like 1, 2, 3, 4, 0, like 0 electron density at the center again. They have 2 nodal planes. You can cut them here and here at the same time. And like what I mean by that is you can kind of cut them with a plane and not hit any electron density at all. This is the only one that's a little weird. It's not 4 lobes, but it's got like a torus, which is the shape of a donut around the middle, and then 2 lobes up in the bottom, up and top and bottom. So these are the 5 different orientations for a d orbital. Right? For L is equal to 2, that's d orbital. The possible m sub L's are -2, -1, 0, 1, and 2. 5 numbers, which means 5 orientations. I don't know which one is which, but these are the 5 orientations. You don't have to memorize the different orientations. You should have a general idea what d orbitals look like. That there are 2 nodal planes, but you don't have to memorize. Hey, that's the xz and the yz and the x squared minus y. You don't have to memorize that. Here's another picture of the same thing. So like I said, depending on the artist, you'll have slightly different pictures of d orbitals. So real quick, you've got this fuzzy looking one with the kind of bulby lobes, and then you've got more kind of stretched out balloon shaping lobes. Depends on the artist. Here's that donut, the torus with the lobe up and down. And here are all 5 d orbitals superimposed on each other. Okay. F orbitals are even crazier. So F orbitals, that's L is equal to 3. And if L is 3, m sub L can be -3, -2, -1, 0, 1, 2, and 3. That's 7 numbers. That means there's 7 orientations. And these are the 7 different F orbitals that exist. Don't worry about these shapes at all. This is kind of advanced stuff. We don't have to worry about it, okay? But just in case you're curious, there you go. They've got like 8 lobes. They've got, 4 nodal planes. It's weird. The equations we use to describe them are a little bit funny. So anyway, don't worry about it. This is just for curiosity's sake. And you know, there's plenty of places online where you can kind of explore these things. I think that link still works, but the one I kind of found recently that works pretty well is this one. And you can actually plug in any energy level you want. So energy level 1, and there's our s orbital, and I think it's spinning right now. You can't tell, but it is. If I switch to energy level 2, there it is, and it's showing the node in between. So it's spherical, but there's this one region right between the inner and the outer sphere that there's no electron density. Let me see if I can show that here. Let's slice it. No. Let's not slice it. The S might, or the P might be more interesting. Here's the P orbital. Here's the PZ. There's the PX goes side to side. The PY is going to go in and out of the screen. So if I kind of try to rotate this sideways, there you go. Kind of hard to see. Anyway. But yeah, you can get to some really crazy orbitals. This is all calculated. So if we go to shell 8, and we go to L is equal to, and so I'm just showing you S, P, D, and F, but it keeps going. Mathematically, you can have lots of crazy stuff happen here. So here is an orbital calculation for shell 8, L4, M0, and they get nuts, but that is what's predicted for like regions where you're finding an electron. It looks nuts, but that's what the math calculates. So I wouldn't worry about this too much. It's just kind of showing you that you can do stuff like this. All right. Hopefully I'm not overwhelming you guys. But that's how interesting orbital mechanics are. So, you know, make sure that this makes sense. These are the quantum numbers that describe the different orbitals. So when n is 1, the only L you can have is 0. That's only s orbitals. That's why there's only an s orbital in shell 1. And there's only one orientation for an s orbital, m0, m sub L0. When in energy level 2, you can have L1 or L0 or L1, an S or P. And for S, m sub L can only be 0, one orientation only. But for P, m sub L can be these 3, so 3 orientations, 3 P orbitals. And you keep going. So here's where D orbitals get introduced. In energy level 4 is where F orbitals get introduced. And so forth. Okay? So remember the rules. Remember how to relate the quantum numbers to the shell and subshell. And there's just another one that kind of shows the same thing. And yet another table that shows exactly the same thing again. Again, the rules are n can be whatever you want as long as it's 1 and it's positive. It's an integer greater than 1, greater than or equal to 1. And then L is based on what n is, and then m sub L is based on what L is. And again, same thing. These are all different kind of figures that show this exact same thing. Last 4 slides. All right, let's try this real quick. Give yourself a break from my talking. And let's try page 197, CT 29, and exercises 1 through 2. It might not be very hard. I think it's just a break. 1 and 2. That's it. Pretty short.
Okay.
It is, yeah.
Oh,
I heard about that on the news.
yeah, on Twitter or something. Should be end of February.
I drove to Tillamook yesterday, or drove back to Tillamook yesterday, in the snow while I was driving through the mountain pass. So, I mean, it was literally snowing. So. Funny, Portlanders do okay in the snow, but you still get a little bit weird because of the hills and stuff. I lived in New Jersey outside Philadelphia. Oh my god. People drive crazy in the snow over there. Like, it snows, nothing shuts down. Nothing. Everybody goes to work. Anyway, it's nuts.
I think that was the only time I
Yeah. Weird weather. Alright. So, I think a lot of you are like, oh, this isn't so bad. This is actually a very common test question. Like, what's wrong with these quantum numbers? So, again, just to make sure, they're saying n is 2, L is 1, m sub L is minus 2. What's wrong with this? Well, if n is 2, the possible values for L are going to be all the integers from 0 to n minus 1. So n minus 1, 2 minus 1 is 1. So 0 and 1 are allowed. That's fine. L can be 1. All right, well, what are the possible values allowed for when L is 1? For m sub L, what are the possible m sub L values? M sub L is all of the integers between positive L and minus L. So there's positive L. M sub L can be anything from 1 to minus 1. So all the integers are 1, 0, and minus 1. That is not one of them. That is not allowed. When L is 1, M sub L cannot be minus 2. So that's the idea behind this kind of problem. You kind of go through the steps, you say what's allowed, what's not allowed. Oh, that's not allowed, so you can't label that this value. So what does that mean mathematically is you can't get a solvable wave function using these three numbers here, these parameters. It doesn't work. Okay. And then over here, exercises for n is 4, what are the possible values of L? Well, if n is 4, it's all of the integers from 0 to n minus 1. So 4 minus 1 is 3. And so that'll be 0, 1, 2, and 3. So if n is 4, 3 is your max, n minus 1. So 4 minus 1 is 3. And it's all the integers from 0 to that max. If L is 3, though, and here's question 2. Here's 1. If L is 3, the m sub L's are going to be what? It's all the integers between positive L and minus L. So between everything between 3 and minus 3. So 2, 1, 0, minus 1, minus 2, and minus 3. So what is L3, by the way? L3 is an F orbital. It's the F subshell. And this makes sense to me because I know that with F subshells, I have 7 orbitals. 3, 4, 5, 6, 7, yeah. All right. We're going to get to the next part, I think. Oh, okay, well, we'll soon get to it. So let's see if people can do this in clickers. If I have, I got one of my little arrows there. If I have, hold on, I didn't start the session. Come on. Okay. So which one of these is not an allowed set of quantum numbers? Ignore the arrow. It's not going to help. All right. So we've got votes B, C, and E. Mostly E, though. And if you voted E, you would be correct. So the problem with E is when n is 3, the values for L can only be 0, 1, and 2, right? N minus 1 is the max for that. Right? All the values from 0 to n minus 1. And if n is 3, your max is going to be 2. So you cannot have L3 when n is 3. It can be 0, 1, or 2, and that's it. So that's what's wrong with that one. The rest of them are actually okay. They all follow the rules. Okay. So, coming back to the Bohr spectrum again. So, you've seen this before. This is, I think, nothing new. We have our energy levels, and we now know that they correspond to that principal quantum number. But where do the subshells come in? Like, I don't see any subshells here. I don't see the s or p orbitals. I don't see any of that. So it turns out that when you're dealing with a one electron atom, like hydrogen, you're never going to see the subshells. The energy calculations get super, super simple, and the subshells happen to be all the same energy as each other. So really you only see energy, the shell energies, and that's it. And that's what we calculate with the Bohr equation. But, so here's really what we're seeing. Even though this is what we did back in, when we did our calculations, we assumed one energy level, 1, 2, energy level 2, energy level 3, energy level 4. The subshells were there, we just couldn't see them. So really what it looked like was this. We have our shell 1, we have our shell 2, which has the S subshell and the P subshell, but they're the same energy, so we can't see the difference between them. And this energy level 3 with its 3 subshells, they were all the same energy. By the way, you're gonna use this term a lot. When we have orbitals that are the same energy, we call that degenerate. Degenerate orbitals. It's a weird word to use, but that's what we've been using for time immemorial. So these orbitals are degenerate, meaning they're the same energy. But, so yeah, there's our ground state, those are our excited states. That's what we see for hydrogen, with one electron. And so, when you do your normal excitation, if your electron's here, you can add energy to get it to go up here, or any other energy level, and then it'll drop back down, release photons, we know all that. So, let's look at multi-electron atoms. What does the energy level diagram look like for a multi-electron atom? So we've seen this already. There are subshells involved. The energies of the subshells are different. This actually happens with multi-electron atoms, not hydrogen. And so let's see, we'll get to that really quickly. So orbitals of a specific type have the same energy, so all 2p orbitals, even though there's 3 of them, they have the same energy with each other. Right? They're still degenerate. The 3d orbitals are the same energy with each other. They're degenerate. So here's what it looks like now. So as soon as you add that second electron, or more, the subshell energies start to change with respect to each other. So there's a little bit of a difference here between 2p and 2s. There's a difference between 3s and 3p and 3d. Within a subshell, though, the orbitals are still degenerate. So these 5 orbitals that exist in the 3d subshell are still the same energy with each other. But now the 3d and the 3p are different. Let's put that. Okay? So we know how to calculate these orders, or not calculate, we know how to figure out the order of these energies. We could do that looking at the periodic table, right? That's what our electron configuration does. 1s2, 2s2, that's what that does. The position horizontally is just so we can visualize it better. It makes no difference whether I put this over here or here, as long as they're at the right energy on the y-axis, okay? So this is way over here just to see it better, that's it. All right, why are they different? Well, multi-electron atoms, when you have a second electron or more, these electrons start shielding other electrons. They basically create these subtle differences between the subshells. And now the subshells have different energies, okay? So, regardless, these orbitals, these positions where we are allowed to find an electron, that are calculated using Schrodinger's equation, getting our wave functions, we can have a maximum of 2 electrons per orbital. A single orbital can hold a max of 2 electrons. We kind of know that already, right? The 1s has space for 2 electrons. The 2s has space for 2 electrons. The 2p has space for 6 electrons. The 3d has space for 10 electrons. You can count the number of electrons based on the number of groups there are in the d block. But if there's only 3 p orbitals, 6 electrons, that means each orbital can hold 2 electrons, okay? So every single one of these lines can fit 2 electrons. Now, there's more to this whole picture of quantum numbers. We learned 3 of them so far, and the first 3 pertain to the orbital itself, like where you can find that electron. There's another quantum number, though, and this one pertains to the electron itself. Not the position, but the electron itself. And it's a really famous experiment. It's really weird. This is another one that's hard to kind of comprehend. But it turns out that if you shoot silver atoms, you have a stream of silver atoms in a vacuum. They're in gas phase, that's how you can shoot silver atoms. And if you shoot them between a really strong magnet, well, these silver atoms are not ions, they're just pure neutral atoms. You would expect them to go right through and hit the backbone. But it turns out they don't do that. If you shoot silver atoms through a really, really, really strong magnetic field, and these silver atoms are not ions, they're just pure neutral atoms, half of them go up, half of them go down. None in the middle. It's a really weird phenomenon. This is a Stern-Gerlach experiment. Maybe, I forgot what this video is. Let's see if it works. No, it doesn't. Okay, it's been 2 years. Well, actually, I think I checked it yesterday, last time. But it does this. So, what is the reasoning behind this? Now, there's more to it than just this experiment, but the only way you can kind of interpret this is that the silver atoms have an electron in them that has what we're going to call a spin to it, spin component. And I've tried describing it to other people before. If you kind of imagine, you know, those gyroscopes where you have this wheel mounted in this little cage, and you use a string and you spin the wheel really, really fast, and then you can kind of set this little gyroscope thing on its end, and it'll stay up. And it'll spin, like if you kind of give it a tilt, it'll spin in one direction. That's kind of the picture of an electron that physicists came up with to describe what's happening here. Because anything that has an electric charge, like an electron does, and if it's moving in a spinning, so if you've taken any electricity and magnetism, any kind of physics class, if you actually loop an electron in a coil and make it go around this coil, what you're creating is an electromagnet, okay? It creates a magnetic field in one direction. And the direction the electron spins creates either a magnetic field that goes up or a magnetic field that goes down. That's kind of the bare bones kind of reasoning behind this. So electrons, in order to behave like this, must have some spin components. They must have like some kind of way that they're spinning or something that opposes this magnetic field or goes along with this magnetic field. And so what the idea is, silver has this lone electron inside that has either a plus 1/2 spin or a minus 1/2 spin. And if it has one or the other, it'll either go up or go down. So electrons, now we know, have this component called a spin. It's not exactly an electron spinning, but that's kind of the easiest way to kind of visualize it. It interacts with the magnetic field the way a spinning mechanism might. And the electrons can either have a spin up or a spin down orientation. And so, this is another quantum number that we are going to assign to this system here. I know a lot of you are like going, what the hell? So the arrow here is a magnetic moment. It's a it's kind of a measurement of how strong the magnetic field it generates is. And so either it's going to go in the up direction or the down direction. That's why the atom, which has the electron in it, went up or down when it went through the magnetic field. And for reasons I'm not going to get into, we're assigning the spin value as a plus 1/2 or a minus 1/2 value. All right, so what that means is it's either spin up, plus 1/2, spin down, minus 1/2. Now, which one it is not a big deal. You don't have to know, hey, it's spin up or spin down. But we'll get into the rules in a second and why that matters. This is a really weird concept, so I don't expect you to be like, I understand it completely. If you want to look it up, feel free. This is where all of our technology, like MRIs, come from. So magnetic resonance imaging comes from a technique originally called nuclear magnetic resonance. And people are afraid of the word nuclear, so they dropped that. But it really comes from looking at the spin inside atoms, the spin of electrons inside atoms. We can use this property of electrons to like analyze a lot of things. So, I'll just give you a quick example. We use NMR, nuclear magnetic resonance, to analyze compounds. So we can dissolve a compound like ethanol. This is pretty simple, but we can dissolve ethanol in some solvent that has no hydrogens in it. So we take solvent that has deuterium or something instead. And so the only thing that has hydrogens is the compound. We'll stick it in our machine, and the machine will give us these peaks that go like that, and then there'll be a big one over here. And it's all from the spin of the electrons in the hydrogen atom on here. And we can see different peaks corresponding to different kinds of hydrogens, like where they are, what position they are in the molecule. And we can basically, we as chemists, we're trained to look at these things and interpret it. Oh, that's this hydrogen, it's got 3 of them, we can read these exactly like that. And it's all from the spin of electrons on these hydrogens. With MRI, they take it a step further and they use computers to convert this signal into an image instead. And so you can image whatever you're imaging in the body. Requires a really, really strong magnetic field to do it. So this is the one where they put you in that really enclosed space, and it makes you feel claustrophobic because they have to generate this really strong magnetic field around your body. So if you have any metal in you, you can't use the machine because it's gonna get ripped out of your body, and it would hurt. Yeah, when we use these instruments, these things, they have such strong magnetic fields. If you have a credit card in your pocket, you get close, it'll wipe your credit card. You know, I've seen people like bring stuff that is metallic inside by accident, and then they'll put it down somewhere where they think that it's far enough away, and then it'll just start inching closer, and then all of a sudden it's close enough where the magnetic field really picks it up, and it slams into the side with such force. Inside the machine there is a coil that is immersed in liquid oxygen to keep it super, super cold. And the reason is because when it's super cold, it becomes a superconductor, so there's all this energy, all this electricity flowing through this coil, and suddenly the shock from the coil discharges the coil and causes all the energy to go into the surrounding liquid oxygen, and it pretty much explodes. I mean, it doesn't explode, you know, where it kills people, but all the gas comes out, and you've, you know, almost destroyed an instrument from a stupid mistake. Anyway, these are really sensitive instruments. They're pretty expensive. That's why MRIs are so expensive. Takes a lot to maintain them. Like you have to submerge the coil that has this giant charge in liquid oxygen, and then to keep the liquid oxygen cold, that is contained in a liquid nitrogen container. So you have to keep re-adding liquid nitrogen so that the liquid oxygen doesn't go away. Yeah, takes a lot of effort.
Yeah, can't it pull in like 5 tons or something like that?
Depends on how close you are. Yeah, so it's I think it's a square of the distance. So the closer you are, the stronger it's going to get, like by a factor of power 2. Yeah.
Mm-hmm.
Yeah. So anyway, we do a lot with this property. This is super, super helpful. And going into why is it plus 1/2, minus 1/2, it's beyond the scope of this class. There's other spins. The nucleus of an atom has a spin. It's all weird, but that's not this class. We're going to focus on the electron spin, okay? So what does this mean to us? Well, an individual orbital, again, can hold 2 electrons only. And here's where the spin comes in. These 2 electrons that are in one orbital must have opposite spin. So if one electron is spin up, plus 1/2 spin, the other one must be spin down, minus 1/2. They must be opposite spin. This is called the Pauli exclusion principle. And this is not actually the whole thing. This is a shorthand version of the Pauli exclusion principle. The other thing is when you put electrons into these orbital diagrams, the ones I showed you on the screen before, where you have the 1s at the bottom, you fill them from the bottom up. You want to put electrons in the lowest energy orbitals possible. And once it's full, then you have to go to the next one higher. But that's Hund's rule. Sorry, that's not Hund's rule. That's the Aufbau principle. Hund's rule is when you get to these degenerate orbitals. So, let me redraw this real quick. So here's energy, here's your 1s, here's your 2s, and after 2s comes 2p. So these are degenerate. Means they have the same energy. So if I have my electrons, and I've already filled up 1 and 2, and notice that I'm doing an arrow that's up and an arrow that's down, and I'm using these half arrows. You don't have to use half arrows, but that's kind of what we've been using in chemistry for a while. You can use regular arrows, it's fine too. But each arrow represents an electron. The up arrow is a spin up electron, the down arrow is a spin down electron. So I would do this orbital next. This orbital is next, and what Hund's rule says is I need to put 1 electron in each degenerate orbital before I pair them. So if I have only 3 more electrons to go, I would not do 1, 2, 3. That's wrong. I would do, let me do this properly. Hund's rule says that if they're degenerate, I put 1 in each. 1, 2, 3, and then if I have more, then I can pair them up. So that's Hund's rule in action, okay? All right, so that's kind of a consequence of electron spin now. We have to keep track of the electron spin. Each orbital must have opposing spins of electrons. Whether you draw them spin up first or spin down first has no difference at all. They're exactly the same. So there you go. So don't do that, not that, basically. So why does this work? Well, first of all, it minimizes electron-electron repulsion. So they have the same energy. So you might think, well, if I do it like this, it's the same energy as if I do this. But when it's like this, these two electrons are in the same orbital. So they're technically closer to each other, and you would have more electron-electron repulsion that way. So it's actually slightly better for them to be in separate orbitals, even though they're all the same energy. There's more. I forgot to wipe these out. So here's another example. Your Pauly, if you have 4 electrons, you would write it like that, not like that. So each orbital, if you're going to put 2 electrons in it, the electrons must have opposing spin. So this is not allowed. Now I say that that's not allowed, like it's illegal, it's never allowed. What I mean is, this is not normal. You can create that, but that's an unusual state. So if you're ever interested in what that does for you, fluorescence and phosphorescence and all that kind of stuff, where you add energy to a chemical and then it glows for a little while. It all has to do with creating these kind of weird energy states, and they persist and they decay in a way that leaks light and kind of crazy stuff, but not for this class. Okay, so this is not allowed normally. Okay, so electrons must be opposing spins when they're in the same orbital. Okay. So which one of these is correct for carbon? I guess we'll not put it on there right now. But carbon has 6 electrons in it, right? It's element number 6. Take a look and make sure you're seeing the full electron configuration, or whether you're looking at the valence electron configuration only. This is including the 1s state, so that's the whole thing. So 6 total electrons for carbon. And both of these are showing 6, but only A is showing using Hund's rule correctly. If you're going to put electrons into degenerate orbitals, so these p orbitals are all the same energy, you have to put 1 electron in each before you pair them up like this. Now this is not an energy level diagram, right? This is just an electron configuration. An energy level diagram shows their actual energies on a y-axis scale. This is like a shortcut. This is just the electron configuration, but like zoomed in to see the orbitals kind of thing. All right. So this is how actually a better way to show these electron configurations without having to show the actual energy axis. We kind of group together orbitals with these boxes like this. So if they're grouped together like this, they're degenerate. They're the same energy. Even though they're all in one line, we know this is the lowest, then comes this, then this is the highest. Okay? If I were to ask you, what neutral element is that? What would it be? Fluorine, exactly. So we're including the inner shell. So this is total electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9. And 9 is fluorine, if it's neutral. Okay. So we have now a new way to represent electron configuration. You can do it the long way, like this. You can do it using the condensed electron configuration. Or you can do kind of an orbital diagram, like this. This is only showing the valence orbitals. You can show all the inner ones as well if you like. But this is, these are all representations of ways to show where the electrons are located. Now, you need to be able to go between like this and this. You need to understand that these 3 p electrons are in 3 completely different orbitals. All right, but that should be, you should be able to work that out with Hund's rule. Okay. So, some conclusions, I guess. Well, if it wasn't already obvious, we've done this with the electron configuration stuff. If they're in the same group, if an element is in group 7, for instance, they have very similar electron valence configurations. Valence electron configurations, put it that way. The inner electrons of pretty much every atom on the periodic table looks exactly like the previous noble gas. And then you just have to add the D and the F electrons that weren't there before. The outer electrons are always going to be in the highest energy level for that element. So, look at arsenic, As, number 33. Its valence electrons are going to be in shell 4. So the 4s and the 4p electrons are going to be the valence electrons. There'll be some 3d ones there as well. And valence electrons are only, so the reason why we name them specifically valence electrons, they're unique, is they're the ones involved in bonding. They're the ones that are furthest away from the nucleus. They're the ones that are going to interact with neighboring molecules, neighboring atoms. They're going to do the bonding. Now, there is this distinction now when we're talking about valence electrons, whether we're talking about a main group element or a transition metal. If you're talking about a main group element, the valence electrons are going to be only the s and the p electrons. So I just mentioned arsenic, number 33. If I were to write the electron configuration for arsenic, it would be, so for arsenic, it would be argon core, and then after that is 4s2, then 3d10, then 4p3. Now, I would actually call the valence orbitals only the ones in the shell 4. These are the only valence orbitals. So this arsenic only has 5 valence electrons. Okay? So you kind of ignore the lower shells if they're full from main group elements. But if I'm talking about transition metals, they're a little bit more interesting, or at least harder to deal with, let's put it that way. So for instance, iron. The electron configuration for iron would be argon core, 4s2, 3d, and then what is it, 1, 2, 3, 6. Yeah. So now, because it's a transition metal, I'm going to include the 3d electrons as part of my valence electrons. So these are all valence now. And so there are 8 valence electrons in iron. So the definition of what is a valence shell or a valence orbital or a valence electron, it depends on whether you're talking about a transition metal, the group in the middle, or if it's a main group element, the S or P block elements. Okay? Yeah.
So for arsenic, why did you write it like that? 4s3.
It's just the way that it comes out of my head when I follow the periodic table. If you go online, if you go to different books, you'll see this is a little bit annoying. You'll see explanations for, oh, you should write 3D here first.
Yeah.
Instead of, in front of 4s. And that really, it matters if you really want to say the electron configuration in terms of what's next in energy.
Okay.
So yeah, definitely the 3D subshell, in this case, is actually going to be lower in energy than the 4s. I'm pretty sure it is. But we're not worried about that right now.
Okay.
So as far as the address, where are all the electrons located, this is correct. Like, when there are 2 electrons in the 4s, there's 10 electrons in the 3d. And you just have to remember that technically the valence electrons are just these, the 4s and the 4p electrons. But yeah, if you are worried about, oh, which one's next in energy, and it doesn't, technically this would go here in terms of if you drew an energy level diagram. But I think in Gen Chem we're not going to care about it.
Okay.
So this is not a big deal at this point. It does get more complicated. We can start to nitpick on things, but I'm not going to worry about it at this point, if that helps.
Okay.
Okay. Okay. The S, P, and D orbitals for the first three shells, you need to get kind of comfortable with them. One thing I kind of wanted to point out, which I didn't before, is even though we draw P orbitals almost always looking like this, that they only really look like that exactly when it's the first or the second shell P orbitals. If you look at shell 3, the P orbitals have these weird little lumps in the inside. So they get complicated just like the higher level S shells do, right? They have those node lines in the middle. It's fine to think of them as like this all the time. That's the general shape. There's two lobes, main lobes pointing up and down, left and right, in and out, something like that. And they might have a little bit of extra detail to it, but we're not going to worry about it, okay? I think your worksheet kind of showed that a little bit in more detail than I can. So if you go back to page 193, you can see it pretty evidently. So that here's the 2p orbital, the normal, dumbbell shape. When you get to the 3p, you start getting weird little, details that pop up that you didn't really notice before. But it's still that overall shape. It's one lobe up, one lobe down kind of thing. So don't worry about the details. Anyway, just know the general shapes. And I think we have a little bit left to do. Yeah, page 196. Questions 16 through 28. This should be fairly simple to do, I think. So digesting everything we've gone over today should hopefully be not too bad. So that's for the subshell, that gives you the shape. MSML is the one that gives you, okay, within a subshell, you have many MSMLs, and those tell you the orientation, which way to point.
Oh, I see.
Okay? probably could use a few more minutes, but I want to talk about some of the answers now. So 16, I think you got the picture, hopefully spherical, the dumbbell shape, and then the 4 lobes for the D. 17, the quantum move that identifies the shape. It's not N, it's the L value that tells you the shape, right? L0 is your S orbital that makes it spherical. L1 is your P orbital that makes it the dumbbell shape, which I erased already. And then the orientation is M sub L. So when you fill in the blanks, I mean, this is just kind of practicing yourself. We know that in shell 1 there's only an S orbital. In shell 2 there's S and P. In shell 3 there's S, P, and then the 3D, right? That, even though that doesn't show up until later, the 3D is allowed in shell 3. So D, and then 4F shows up. So L is 0 only here. Here it can be 0, 1. Here it can be 0, 1, or 2. And here it can be 0, 1, 2, or 3. 20. Given the above table, and remembering that the quantum number L tells you which subshell can fit the following statement. So this is just kind of not correlating, but assigning these orbital types to the quantum number that goes with it. So S goes with 0, P goes with 1, D goes with 2, L goes with 3. So what happens to the size as N increases? Well, they get bigger. What happens to the energy? The quantum number, which quantum number determines the energy of an orbital in an atom with more than one electron? So the quantum numbers that tell you the energy are going to be both N and L, right? N the shell, L is the subshell. You need both to get the full picture of the energy. M sub L is not going to tell you anything because within a subshell, so in subshell 3, which is an F orbital, there's going to be 7 F orbitals, but they'll all be degenerate. They'll all be the same energy. So M sub L doesn't tell you the energy, okay? Just N and L. And then this is going through M sub L values 0, 1, 0, minus 1, 2, 1, 0, minus 1, minus 2 here. And how would we label them? Well, for an S orbital, there's only one kind of S orbital, so I just label it S. That's it. But for a P orbital, there's 3 possible ones. There's going to be minus 1, 0, and plus 1. What real world labels can I give them? Well, they go in the X direction, the Y direction, and the Z direction. So I can call them PX, PY, PZ. And then for the D orbitals, I'm not assuming you need to know that. Don't worry about it. But if you go back to the chart up here, they actually give you the label names. Again, don't memorize them. But Z squared, X, Z, Y, Z, X, Y, X squared, Y squared. Where do they come from? Well, some of them I can tell you. The XZ1 is the lobes that are in the plane that the X and the Z axes form. And here the YZ plane, here it's the XY plane. I can't really tell you where these labels come from, but it's just another linear combination, which is math. So it's all linear algebra stuff. Okay. But don't worry about memorizing that. That's no big deal. All right, 24. Okay. Which orbitals have a plane that includes the origin where the probability of finding the electron is 0? So these are nodal planes, angular nodal planes. The D and the P orbitals and the F orbitals all have these, where they're asking for S, P, and D. The S orbital doesn't have this, right? At the nucleus, you can find an electron. Some of you might be thinking, how is that possible? How can you find an electron at the nucleus? Well, remember, we're talking about an electron as a wave. So it's not just there, it's a lot of places at once. So it's weird, but that's how you have to think of these things. An electron could be at the nucleus. And don't think of the nucleus as this solid chunk of matter. There's going to be lots of empty space between the neutrons and the protons too. Anyway, don't worry about that too much. How many nodal planes do S orbitals possess? 0. Okay, no nodal planes that go through like the origin. P orbitals have 1. Right? If I draw any p orbital, you can count the 1. So there's the one that goes through right there. If I draw it this way, there's the one that goes through this way. And the one that goes in and out of the board, the board is the nodal plane. D orbitals have 2 nodal planes. Right? So if I draw any d orbital, the generic one kind of looks like that. There's going to be a nodal plane this way and a nodal plane that way. So d orbitals have 2 nodal planes. That's kind of how you identify them. Now those are angular nodal planes. There's another kind of node called a radial node. And these are the nodes we saw when we looked at the different shells, right? So you started with a 1s orbital. It was just a sphere. But when we got to the 2s orbital, here, so we do the 1s orbital, it's just a sphere like that. But when we get to the 2s orbital, we look inside, there's kind of, it's going really fast, hold on. There we go. There is a region right around the middle that there is no electron density. And that is a radial nodal plane, or radial node, I should say, not plane. And so, you get nodal planes after you get past that first shell where those orbitals start existing. So for the 2p and the 3p, we go back to see what a 2p and a 3p look like. All right, here's the 2p. This is where you start seeing the p orbitals, shell 2. You have the angular nodal plane, the one that goes through 0, but there's nothing else. These spheres are just kind of, not solid spheres, but there's nothing interrupting them. But when you get to the 3p, now you get that weird angular nodal thing. So you have a lobe here and a lobe here, and you have your nodal plane in the middle, just like before. But you've also got this radial node that kind of splits these two pieces, kind of like the s orbital did. So you can start seeing these radial nodes when you get to higher shells for any of the subshells. Okay. Okay. Now, what else? I guess that's it. Okay, so here's the frustrating thing about this. There's only so much we can get to with this before we get hit by the brick wall of math where we just don't know enough. Me too, I'm included. So we can test you up to a certain amount of stuff, and it may seem, oh, it's arbitrary. It is a little bit arbitrary. We're testing on this stuff because we can. But we are teaching you with the assumption that you would be able to go on and take more chemistry later, even if you're not. So this is your intro to this concept. And if you do take more chemistry, you'll have a basis for understanding the more advanced stuff. That's why we're teaching this to you, okay? But this is as far as we're going to go with all the quantum mechanics stuff. I want to go back really quickly because I talked about that Stern-Gerlach experiment, the one with the silver atoms. That's how we discovered the spin of the electron. And I want to show you why it worked the way it did. So first, let's talk about silver atoms, Ag. The electron configuration for silver. And this is going to be frustrating because I'm going to teach you something you're like, it doesn't go along with what we were taught. Silver has a krypton core. So the inner electrons look just like kryptons. And then 5s2 is what I would normally put. And silver is the 1, 2, 3, 4, 5, 6, 7, 8, 9th over. So 4d9 is what I would think that is the correct electron configuration for silver. That is actually not correct. So this is what the rules that I taught you would predict for silver. The rules that I taught you are not 100% perfect. There are other things that you have to understand in order for this to make sense. But the real picture of silver's electron configuration is krypton 5s1 4d10. Now, I can explain it with a little bit of hand waving, but the idea is the energies of the 5s subshell and the 4d subshell are really close. In fact, the 4d is still slightly higher. But they're so close that it actually is better for one of the electrons that's in the s subshell to go and occupy the d subshell, because actually having everything subshell full stabilizes somehow the atom a little bit more than having it only partially full. And in fact, it's full and half full states that are actually favorable. So if I move one of the electrons in the s subshell over to the d, I get this. The d shell is now full. The s subshell is half full. This is actually a lower energy state for silver. So that's actually what silver's electron configuration is. I'm not going to quiz you on this on an exam, but this is just happens to be what silver's is. Now, given this, if you drew the orbital diagram for silver, what is it going to look like? I'm just going to do the valence one. So I'm going to ignore all the krypton stuff. It's going to kind of look like this. You're going to have, well, actually, let's not even do the energy one. Let's just do the partial orbital diagram. So we've got the 5s, and then we've got the 4d. And remember, d orbitals come in sets of 5. 1, 2, 3, 4, and 5. 5 boxes. And those are full. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then the 5s orbital is only half full. So that's what the electron configuration of silver looks like. This silver atom has a single electron that is not paired. That silver electron could coincidentally be spin up, or it could be spin down. The fact that I did spin up, it was a coincidence. You could write spin down as the same. But this is the reason why when you shoot a silver atom through a strong magnetic field, if the electron in it is spin up, it'll go one way. If it's spin down, it'll go the other way. If you do the same with another atom, if I did it with, for instance, cadmium, if I tried to do this experiment with cadmium, cadmium's electron configuration is 4, so krypton, 5s2, 4d10. And so if you were to do the orbital diagram, just like we did for silver, everything is full. And then this is full too, 5s, 4d. There are no unpaired electrons in this. Everything's paired up. And so if I were to shoot cadmium through a really strong magnetic field, it would just go right through. It would hit the center of the detector. It would not deflect like silver does, where half of it goes up, half of it goes down. And that's because of the presence of this one lone electron that is unpaired. Cadmium doesn't have this. So we have lots of experiments that verify this kind of spin effect of electrons. It's pretty interesting stuff. So, what else can I say? Just kind of wanted to bring it back. I think that's it. But let's kind of go over this real quick, make sure this makes sense. So, looking at this thing, which orbital are we looking at if it's in the third shell? So, most people said B. It would be B. Yeah. If it's in the third shell and it's a round-shaped orbital, it has to be an s orbital. If it's in the third shell, it's the shell 3s. It's not a big trick or anything. So, what would this be? see a lot of furious clicking, but then the numbers don't change. So I don't know if it's flashing red. Either there's a connection problem or a battery issue. But anyway, we have a couple votes for all over the place, but most people say E, and it is E. So this is definitely a p orbital. How do we know? Well, one, it's that general shape, the two lobes. If you weren't sure, a single nodal plane cuts it. That's identifying a p orbital as well. And this is in shell 4, so it's a 4p orbital. What about this one? So, it is definitely a d orbital according to the, here we go. It is definitely a d orbital, but it is a 3d orbital since it's in the third shell. So, on the left, actually I'm not going to do the left, we'll just skip that one. The left one is definitely a 3p orbital. What about the one on the right though? So this one looks a little bit like a P, but it's not a P orbital. It's actually got that donut around the middle. That's the one I kind of pointed out is a D, kind of weird D orbital. And that is one of the D orbitals. And if it's in the fourth shell, it's the 4D orbital. One of the 4D orbitals. So, you know, you'll need to do that, identifying orbitals. You'll need to draw orbital diagrams. So if you had to draw the full orbital diagram for iron, you could start with an electron configuration if you want, but you need to be able to draw it out as well. So here is the full orbital diagram for iron. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then if you count over for iron, there's 6 electrons in the 3d. So you would do 1, 2, 3, 4, 5, and then the 6th one you'd pair up, because d orbitals come in sets of 5. And once you've done that, I think the condensed diagram is so much easier. It's the argon, 4s2, 3d6. So, unpaired electrons. This is a consequence of understanding orbital diagrams. You need to understand, well, which things have unpaired electrons, which don't. Why is that important? So we can actually measure unpaired electrons. They interfere with, or they interact with magnetic fields. We can measure these unpaired electrons directly. So which one has more unpaired electrons? Okay, it's time to go, I guess. All right. You don't have a guess, it's okay. So it turns out, that's okay. I think it was vanadium. Is that it? Yeah. Oh no, it's manganese. I'm looking at it. Oh yeah, it's manganese. If you do the electron configuration for these things, they all are similar. They have the argon core, 4s2, 3d something. So for vanadium it's 3d3. For manganese it's 3d5. For iron it's 3d6. And you have to do the orbital diagram configuration, which is not here. For manganese, if you do it, you'll end up with, in your 3D section, 1, 2, 3, 4, 5, and you'll have 5 unpaired electrons. For vanadium, you'll only have 3d3, so you'll have 3 unpaired electrons. These will be gone. For iron, you'll put a 6th one, and that 6th electron will go down here, so you only have 4 unpaired electrons left. So it is manganese in this case. All right, we'll review all this on Wednesday, because I think it's been a long day. So we'll talk about Wednesday. I think this is pretty much what's going to be on the exam next week, up to this. We'll review it some more Wednesday. We'll have a quiz on previous stuff, last week's stuff. And then we'll get ready. I think we'll do the full review on Monday, because our exam is on Wednesday next week. Okay. Any questions? Everybody's dead. Okay. Sorry, there's a lot of hand waving in this lecture. Yeah. What's up?
I remember a lot of this from like my high school chemistry class.
Yeah, they tend to go over it quite a bit if
Yeah.
you've taken high school chemistry.
For
It's an easy
I remember
quiz
it.
on, you know,
I
quiz.
remember it being a lot simpler.
So for 24,
Uh-huh.
Okay, so 24 and 28 I have questions on. So,
Okay.
The radial nodes don't appear until after 3P?
So, the radial nodes will appear after the first time that subshell appears. So 2P is the first time you see the P's, right?
Okay.
So you won't see them in 2P, but you'll see them in 3P.
And then you'll keep on seeing them after
You'll
that?
see more, yeah, yeah.
Okay.
So for S, 1S is the first time you see this S subshell.
Okay.
So you don't see them in the 1S, but you'll see them in 2S, 3S.
Okay, so from 2S, for this one, it'll be 2S and above?
Yeah.
Okay. Okay.
And then D's, you know, you don't see them in the 3D because it's the first time you see the D's. You'll see them in the 4D and the 5D.
Okay. Okay, that makes more sense. Thank you.
We're honestly not going to do anything with the whole radial node concept.
Oh, really?
It's well, I mean, I can quiz you on that and that's it. Like, but there's no benefit for us at the moment. We're not going to use it for anything. So that's why I'm saying, you know, we're teaching you this as an intro for future classes, maybe, if you're going to take more. You know, so you know that they exist. When they bring them up, you'll be like, okay, I've seen that before.
Are we gonna get our quiz grades back from last week?
I did not finish them in time, so I'm gonna probably give them back to you on Wednesday.
Okay.
You probably walked in late. The reason there's old exams up here is one of the quiz or exam questions was graded incorrectly.
Oh, okay.
So was it 11 or
It was 9.
It was 9. So 9, I graded it as E incorrectly. The answer should be C.
Okay.
So it's here, just so you can remember which one is which. It's this one. It goes with this,
Uh-huh.
but the answer should have been C.
Uh-huh.
So if you wrote C, you can bring it back. I'll give you points for it.
Okay, cool. Well, that-
For which question?
9. The exam.
Oh.
Oh, you walked in late too. So there you go. It should be your punishment. Anyway, you got it. Yeah. So
Yeah.
here, put it in the pile. I'll grade that. And here, let me give you this.
Thank you.
And let me give you this. Crystal, what are you?
Yeah.
Yep. This is my least favorite lecture. Even though it's kind of interesting, it's like, and I can't tell you more, you know?
Yeah, and it gets kind of interesting because spin is how quantum computers work.
Yes, yeah, that's true. And it's interesting.
Yeah, it gets even weirder.
It's
weirder with.
so like the whole NMR thing. It's also weird because when you have a sample, it's like supposed to be 50-50 whether it's spin up or spin down, but in reality, there's slightly more of one than the other, and that slight difference is what lets you see a signal. Or it's like hard to explain that too. You know, it's all probability. It's all weird.
So is that like the same concept as like when you have a fan and you put in like the fan spins one way because you have positive going through one way, and then if the fan spins the other way, it's negative going through the other way on the circuit?
Oh, if you I guess so. I think they have electronics to make sure it goes in one way though.
Like for the fans on the ovens, like if you put
Have you wired them in incorrectly?
well, not, well, that as well, but if you put, for ovens, the fans don't turn on through electricity.
Uh-huh.
It turns on through temperature, so like, if it's hot, then it'll spin one way, but if it's cold, then it'll start to spin the other way, but it has to be extremely cold.
Oh. I don't know, actually.
I have no idea
There
about
must be
that.
a relay that switches it on and off. 'Cause
Okay.
And then just a sensor that expands, contracts, or
But,
something.
yeah, I mean, in a basic AC circuit, no,
Like if it's,
I can't
not
remember.
a parallel, but
I'm
a
not
series.
I'm not an electronics person exactly. I know digital circuits. I don't know the analog, which is what you were talking about very well.
Okay.
That stuff is like magic to me. The people who are really good at that stuff is like crazy. You have a question? The same thing?
Yeah, if I got it wrong, do I have to submit?
I'll take it. Yeah, and I'll give it back to you
Okay.
Wednesday or
Oh,
something.
I mean, like, like.
Oh no no no! You got it.
So
No,
I can
no,
get
keep the
answer.
points. Keep the
Okay,
points.
cool.
No no
Thank
no.
you.
Yeah.
Thank you.
It gets really weird at the quantum level. Like